Hi, I'm Nusrat.
Hi, my name is Iqra.
Hi, I'm Saidah.
This video is about the ideal gas law. The concept of an ideal gas is an approximation that helps us model and predict the behaviour of real gases. We will be looking at three variables, which are temperature, pressure and volume. The formula which combines these variables is the ideal gas equation, PV equals nRT, where P is pressure, V is volume, N is the number of molecules, R is the gas constant, and T is temperature.
A property of ideal gases is that they are randomly moving points that interact only by elastic collisions. Generally, a gas behaves as the ideal gas at a higher temperature and lower pressure as the potential energy due to the molecular forces becomes less significant compared to the particle's kinetic energy. Examples of ideal gases are noble gases like helium, neon, argon, krypton, and xenon.
Although the ideal gas law was originally derived experimentally, it can also be derived theoretically from statistical mechanics. It was first stated by Emile Clapeyron in 1834 as a combination of the empirical Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law.
We're going to conduct experiments. The first experiment uses a spray can and a thermometer. We will release the air from the spray can. We will then use a thermometer to record the temperature dropping.
The next experiment focuses on how volume affects pressure. The apparatus required is a syringe and pressure gauge. When you decrease the volume in the syringe, the pressure increases. This is because in a smaller volume there are the same amount of particles in a smaller area, so there are more frequent and successful collisions. In this experiment, the temperature is the constant. In order for us to keep the temperature the same, we will wait for the temperature to cool down and revert to the initial value.
The first results table shows our raw data from the experiment. We then worked out the corrections using digital calipers. Through this, we were able to remove systematic errors in the data and make it more reliable. We then plotted the corrected data. So when we halve the volume, the pressure doubles, and if the volume reduces by 3/4, the pressure increases by 4/3. This can be expressed in the relation P is proportional to 1/V.
The final experiment focuses on how temperature affects volume. For this experiment, you will need a balloon and liquid nitrogen. Place the balloon into the liquid nitrogen, making sure you are wearing cryogenic gloves. The liquid nitrogen makes the balloon colder. This means the temperature drops and so the volume of the balloon decreases. This is because it will counteract the change in temperature.
This is Mr. Daniel Darby-Lewis, a PhD student of theoretical physics at UCL. Hi Daniel, thank you for joining us today. So what is the importance of the ideal gas law?
The ideal gas law can describe the behaviour of any gas, assuming certain things about it. And it can tell you about its pressure, its volume, and its temperature, and how they all relate to one another using fundamental constants.
How does the liquid nitrogen experiment link to the ideal gas law?
In the liquid nitrogen experiment, a balloon is taken and placed into liquid nitrogen, and you see the balloon shrink and shrink and shrink until it looks almost like there's nothing in there. And then as soon as you take it out again, it starts to warm up, it expands again. And so it links to the ideal gas law because volume is proportional to temperature as long as pressure remains constant. And because the balloon squeezes on whatever inside, the pressure is remaining roughly constant. Therefore, when you decrease the temperature, the volume also decreases. The syringe experiment uses a syringe and a pressure gauge to decrease the volume of a set amount of gas while maintaining a constant temperature. If you map out the curve formed by the pressure and the volume ratio, you can use this to calculate the gradient of a line. And the gradient of that line relates to the gas constant.
There are two versions of the ideal gas law, one with a lowercase n and r, and one with a uppercase N and kb. What is the difference?
These two are the same formula, they've just had the constants and then slightly rearranged. So lowercase n is equal to uppercase N divided by Avogadro's constant, which is Na. Avogadro's constant is a number, just like a dozen, but instead of being a dozen, which is 12, it's some number times by 10 to the 23. So it's an incredibly big number. Capital N is just the number of molecules, lowercase n is the number of moles, which is the number of Avogadro's constant's number of molecules. R is equal to Kb times by Na. So what happens in the rearranging is the NA in the R is taken out and put into the lowercase n to turn that lowercase n into the uppercase n, and then you're left with Kb. Now R is the gas constant and Kb is called Boltzmann's constant. And Boltzmann's constant is a fundamental constant which is found all throughout physics, from quantum mechanics to statistical thermodynamics, and it expresses some very important properties about our universe.
What does physics mean to you?
Physics is about learning more about the world around us. It means exploring the world we live in and finding out ways that we can describe the nature of our reality using mathematics, using empirical equations, and just figuring stuff out based on our curiosity about the world around us.
Okay.
Can we stop now?
Iqra from statistical mechanics.
So, what is the... Oh, I forgot the question.
That's right, that's right.
It was first stated by Emil Clapeyron in Azicon.
So we're gonna finish this now.
Created a child on my own. No! I need to kill my child. Why